Flying the traffic pattern in a seaplane is not that much different than flying one in a land-based airplane. The legs are the same, and the altitudes may be flown at a comparable height. Where the traffic pattern differs is in the fact that you won't have the numbers on the runway to use as a reference, and in many cases, you can adjust your pattern so that your final approach will be directly into the wind.
One of your primary concerns when preparing to land on the water is the obstacles that may be apparent in and around the water. Obstacles may be moving traffic on the water, such as boats and other seaplanes, or they may be stationary and partially submerged, like floating logs. While you may be able to obtain some information about an established seaplane base from a sectional, an airport facility directory, NOTAMs, or through the Seaplane Pilots Association's Water Landing Directory, these sources are only accurate at the time they are published. Conditions and obstructions are subject to change more rapidly when influenced by water. Prior to takeoff or landing on any body of water, it is highly recommended that you survey the area. From the air, a survey can be performed from an appropriately safe and legal altitude prior to entering the traffic pattern. This survey should continue throughout the pattern and until safely secured at the dock. The before takeoff survey should start at the dock and continue until you are safely clear of any obstacles along the shoreline. Thorough scrutiny should be given to the area to assure not only that it is clear, but that it will remain clear throughout the takeoff. Prior to takeoff, you should perform a pre-takeoff check of the aircraft. Unless this check is performed before entering the water or untying from the dock, you will be on the move as you complete your run-up. Be certain that this can safely be performed under the existing conditions and keep a good lookout for obstacles that may be on the move or otherwise. You will perform a normal takeoff directly into a light to moderate wind. If the wind is too light, a glassy water technique will be required. If too strong, a rough water technique may be required. These techniques will be discussed in a moment. During a seaplane takeoff run, there is a point of greatest resistance while you transition through the plowing attitude. This is referred to as the hump because the increasing and decreasing effect of water drag causes a hump in the plotted drag resistance curve. After the hump is passed and the seaplane is traveling on the step, water resistance decreases. Do not apply too much back elevator pressure during the planing or liftoff phases, or you will force the stern of the floats deeper into the water, creating a strong resistance and appreciably retarding takeoff. Conversely, if you apply insufficient back elevator pressure, the bows will remain in the water, which also results in excessive water drag. Glassy smooth water increases the adhesive properties of the water's surface and creates additional water drag that must be overcome. This can increase your takeoff run and may not allow the float to unstick from the water without using proper technique. Whenever the water is glassy, you can make your takeoff less difficult by making the takeoff run across the wakes created by motorboats. If boats are not operating in the area, you can create wakes by taxiing the seaplane in a circle and then taking off across these self-made wakes. You can reduce water drag after the seaplane is on the step by applying sufficient aileron pressure to raise the wing and lift one float out of the water. By allowing the seaplane to turn slightly in the direction the aileron is being held, rather than holding opposite rudder to maintain a straight course, considerable aerodynamic drag is eliminated, aiding acceleration and liftoff. When using this technique, exercise great care so as not to lift the wing to the extent that the opposite wing strikes the water. During rough water takeoffs, apply slightly more back elevator pressure than on a normal takeoff to raise the bow to a higher angle. After you begin to plane, the seaplane will bounce from one wave crest to the next. To correct this situation and to prevent a stall, use smooth elevator pressures to set up a fairly constant pitch attitude that will allow the aircraft to skim across each successive wave as speed increases. It is important that control pressure be maintained to prevent the bow from being pushed under the water surface or stubbing its toes, which could result in capsizing the seaplane. The advisability of canceling a proposed flight because of rough water depends on the size of the seaplane, wing loading, power loading, and most important, the pilot's ability.
The landing approach procedure in a seaplane is very similar to that of a land-based airplane and is governed to a large extent by pilot preference, wind, and water conditions.
Under normal conditions, you can land a seaplane either power off or power on. However, power on landings are recommended in most cases because this technique gives you more positive control of the seaplane and provides a means for correcting errors in judgment during the approach and landing. So that the slowest possible airspeed can be maintained, you should accomplish the power on landing with maximum flaps extended. Trim the seaplane to the manufacturer's recommended approach speed and make the approach similar to that of a land-based airplane. Touch down on the water in a pitch attitude that is correct for taxiing on the step, or perhaps a slightly higher attitude. This will result in the floats first contacting the water at a point aft of the step. Once water contact is made, close the throttle and gradually apply back elevator pressure to reduce the tendency for the seaplane to nose down and dig its bows in due to increased drag of the floats as they contact the water. It may be desirable at times to remain on the step after touchdown. To do so, merely add sufficient power and maintain the planing attitude immediately after touchdown. Flat, calm, glassy water is perhaps the most deceptive condition that a seaplane pilot will experience. The calmness of the water has a psychological effect in that it tends to overly relax the pilot when there should be special alertness. Consequently, this surface condition is frequently the most dangerous for seaplane operation. From above, the mirror-like appearance of smooth water looks most inviting and easy to land on, but as many pilots have suddenly learned, adequate depth perception may be lacking. Even experienced pilots misjudge height above the water, making timely roundouts difficult. One technique to assist in judging the height is to make the approach and landing near the shoreline so that it can be used as a reference for judging height above the water. Another method is to cross the shoreline on final approach at the lowest possible safe altitude so that a height reference is maintained to within a few feet of the water's surface. Using this technique, you must cross this last visual reference, or LVR, with your speed, altitude, and descent under control and as desired. Failing to arrive in your LVR box in a stabilized manner may necessitate a go-around. During the final approach, fly the seaplane at the best nose-high attitude, using flaps as required or as recommended by the manufacturer. Establish a power setting and pitch attitude that will result in a rate of descent not to exceed 150 feet per minute and at an airspeed approximately 10 knots above stall speed. Upon touchdown, apply back elevator control pressure as necessary to maintain the same pitch attitude. Reduce or close the throttle only after you are sure that the aircraft is firmly on the water. Cues for this include the feeling of a slight deceleration force, the observance of a slight downward pitching moment, and the sounds of water spray striking the floats or other parts of the aircraft. Bear in mind that this type of approach and landing will usually consume considerable landing distance. It's very difficult to describe an ideal rough water procedure because of the varying conditions of the surface. In most instances, though, the approach is made the same as for any other water landing. It may be better, however, to level off just above the water surface and increase the power sufficiently to maintain a rather flat attitude until conditions appear more acceptable, and then reduce the power to touchdown. A nose-high touchdown with power on the back side of the power curve may also be effective in keeping the bow of the floats from digging into the waves. If severe bounces occur, you should increase the power and search for a more ideal landing spot. Because of restricted or limited areas of operation, it is not always possible to take off or land the seaplane directly into the wind. Such restricted areas may be canals or narrow rivers. Therefore, you must acquire skill in crosswind techniques to safely operate in these areas. The forces developed by crosswinds during takeoffs or landings on water are almost the same as those developed on land. Directional control is more difficult because of the more yielding properties of the water, less surface friction, and lack of wheels or brakes. Weather vaning and side drift are an issue and must be addressed. If too strong, the inertial forces that these can produce may cause the airplane to tip such that a wing catches and a water loop occurs.
Because of the lack of clear reference lines for directional guidance, such as are found on airport runways, it's difficult to quickly detect side drift on the water. Fortunately, early detection of side drift is not really essential because the seaplane takeoff and landing can be made without maintaining a straight line while in contact with the water.
One technique sometimes used to compensate for crosswinds during water operations is the same as that used on land. That is, by lowering the upwind wing while holding a straight course with the rudder. This creates a slip into the wind to offset the drifting tendency. Another technique used to compensate for crosswinds is the downwind arc method. Using this method, you create a sideward force through inertia that will offset the crosswind force. This is accomplished by steering the seaplane in a downwind arc. Plan an arced path and follow this arc to produce sufficient centrifugal force so that the seaplane will tend to lean outward against the wind force. When operating off a small body of water, confined area techniques must be used. An acceptable technique may be to begin the takeoff run while headed downwind and then turning so as to complete the takeoff into the wind. This may be done by planing the seaplane while on a downwind heading, then making a step turn into the wind to complete the takeoff. You must exercise caution when using this technique, since wind and centrifugal force will be acting in the same direction and could result in the seaplane tipping over. Landing in a confined area requires an appropriate survey of the area. You must determine the path for the approach and landing based upon the conditions observed. A turn after landing as the aircraft decelerates may also be required, and the path for this must also be considered.
While never desirable, an emergency approach and landing in a seaplane can provide you with more options than in a land-based airplane. You can, of course, land on the water, but dry land is also an option.
For an emergency landing on the water, you will need to select the optimum location for your touchdown. Water with some movement would be preferable to a glassy surface, but you really don't want it to be too rough. You also need to consider where you will end up after you are floating in the water. Without an engine, you will be held at the whim of the wind and the current. You may be able to adjust your destination with your paddle in some conditions, but this may only help a bit. Set up the approach for your intended point of landing much as you would with a land-based airplane. Keep in mind that your seaplane will likely have less gliding performance than its land-locked equivalent. Maintain the recommended speed and configure the aircraft as suggested by the manufacturer. Begin your flare at an appropriate height for the seaplane and allow it to settle onto the water. Take care so as not to run out of forward energy for the flare before touchdown.